In this final part of the exercises on routing, we will have a look at reservoir routing. In reservoir routing, we also start with the equation, the continuity equation, ds over dt, so the change of storage over the change of time is equal to what comes in minus what comes out. If we write this in a discrete way, we have the equation that we had earlier already, so the difference between the storage at the next time step and the storage at the current time step divided by the time step, and then the average of the inflow minus the average of the outflow. Now, the orange values that are mentioned here, so Sj, Ij plus 1, Ij and Qj, they are known. On the other hand, Sj plus 1 and Qj plus 1 are unknown, because we don't know at what level the reservoir is, and we don't know what the corresponding storage and the corresponding outflow is. So if we rewrite that, we get that the left-hand side are two unknowns, and on the right-hand side, all the factors that are actually known. To get the storage and the outflow out of this equation, we need an additional relationship between S and Q. And this will be our storage function. Now, our storage function will be based on the fact that both S, the storage, and Q, the outflow, are actually a function of the water level above, in this case, the wear crest. And the storage is just based on the geometry, and the outflow is actually based on the wear equation. Now, if we know Q as a function of H and S as a function of H, we can get all of different points that correspond with a certain value of H and get a combined graph or a combined function which relates Q to S. And that's what we are going to do here as well. Now, we know from our assignment that we have some characteristics of the reservoir. We know that above the wear crest, which we will be looking at, we can go up from 0 meters, where it is at the start here of in the exercise, and we can go 2 meters up. More is not possible in this case. That's one of the assumptions. And we know also that our reservoir, has actually a trapezoidal cross-section. So at the base, at the small base, being the part where the water level is 0 meters above the wear crest, so actually at the wear crest level, our reservoir has a width of 119 meters. And it increases all the way up to where H is maximum, so the water level above the wear crest is 2 meters, and there you have actually at that time the large base B, which is equal to 119 plus factor 1 multiplied with, in this case, 2, so 121. So our reservoir above the wear crest goes from 119 to 121 meters. The length of the reservoir is 10 kilometers. Based on this information, we can actually calculate the storage above the wear crest depending on our H value. Similarly, we can also use the wear equation, where we know the L factor, so the length of the wear, and the C factor, which is to take into account the discharge coefficient. And we know these values. The length is 20 meters, the discharge coefficient is 0.6, and based on the wear equation, we can calculate Q values also based on the H value. So we know S as a function of H and Q as a function of H. And based on that, we can get our storage equation. So in this case, if we have S and Q as a function of H, we can actually write, for example, based on the value that we get for 2 as j plus 1 over delta 2 plus q j plus 1, a corresponding q value and s value. And in that way, we can solve this equation. So we need to define in the first question the storage outflow function. And I've prepared an Excel sheet already where we have again the equation with our unknowns and our knowns, the information about the reservoir, and the where's equation. I've also put here some values of b, the small base, x, the length of the reservoir now expressed in meters, the wear crest width 20 meters, and the discharge coefficient 0.6, because we will be using those in our equations. Now, we know that our H value, so the water level above the wear crest, can go from 0 to 2 meters. So let's write this in this column already. So we go from 0, and let's add some digits behind the decimal sign. And we go, for example, first in steps of 0.05. So we go from 0 to 2 meters, like this. So these are all possible H values above the wear crest. So the water level above the wear crest can be 0, 0.05, 0.1, 0.15, and so on and so forth. And we can calculate a corresponding storage value. In this case, it's a volume, so in cubic meters, based on this H value. How? Well, we know that the storage is the volume that corresponds with a certain water level. And our section is trapezoidal and we have a certain length. So in this case, if we take into account the trapezoidal section, we know that it is small base, plus the large base, which will be the small base plus our H value, and this multiplied with the H value again divided by 2. This is the trapezoidal section, but we have also a length of 10 kilometers, so we need to take into account our length as well, x. Now, in this case, our storage is 0, which is logical because we don't have any storage above the wear crest level, as our water above the wear crest level is 0. Now let's fix some of these values because we're referring to b, small b, and also here small b, and in this case x. So let's fix those. If we drag those, we get all of these values for our storage above the wear crest. Now, we can also calculate Q values. Q values, which will be in cubic meters per second. This will be based on our wear equation. So it will be equal to 2 over 3 multiplied with C multiplied with L, and then multiplied with, in this case I will say 2 multiply with 9.81 to the power 0.5, and then we multiply with our water level above the wear crest to the power 3 divided by 2, like this. Again, of course, if we're at the wear crest level, there is no outflow, so that's also logical. Let's make sure that we refer to fixed values here. So F4 for the C value, F4 for the L value, and that's all. Let's take 4 digits behind the decimal sign, and we get flow values corresponding with a certain H value. Now, we could make a graph out of this already. Let's do that quickly, just to, let's make this a little bit nicer first. Like this. So a scatter plot, which will be in this case, of course, just a linear equation. Let's call this S is equal to function of H, like this. So that's just a representation of our storage as a function of the water above the wear crest. Similarly, we can also make a graph for Q as a function of H. So again, a scatter plot. That's not a linear one, of course. And this would be Q is equal to function of H, like this. Of course, in both graphs, I still need to add a title of the axis. So this will be H in meters, and this will be S in cubic meters. And similarly here, this will be H in meters, and this will be flow or Q in cubic meters per second, like this. Now, what we actually wanted was a relationship between S and Q, so we could just select those two, like this, and we could also add this is not good, so let's delete this. Let's try it again. Could be that I need to change. This looks better already. Let's move this, and we will call this storage equation, because this is our additional equation that we have between Q and H. Like this. Sorry, not between Q and H, between Q and S. And so on the horizontal axis, yes, we will have storage, of course in cubic meters, and on the vertical axis we have flow in cubic meters per second. So this is our storage equation. Now, if we look back also to our equation over here, we actually see that we don't have S and Q separately. So if we calculate, we will have these values. These are known. This is unknown. So we will get a value out of this equation, which is the sum of those two. And out of that one, we will need to extract the Q and the S value. So actually, we will sum up these to get actually this value. So we say, okay, in this case, let's call this 2S over delta T. Let's insert this symbol like this. Plus Q, and that will be of course in cubic meters per second. And so we just sum up 2 times S divided by our time step, and our time step will be 3,600 seconds or 1 hour, because that was also the time step that we will use in our application afterwards, plus the Q value based on this equation. So if we drag this, we get actually the values of our left-hand side part of the equation. Now, why do we need that? Well, now we can relate these values of the left-hand side with a Q and an S value. So if we get a value out of this equation, we can get the value of Q and S. Now the good thing is that we can, for example, add here an additional line, and let's say that we use this one, and let's color this one in yellow, and we will use that one to fill in a certain H value, to search for a certain H value, which corresponds with the value of the left-hand side of the equation, the unknown side of the equation, and we get the corresponding S and Q values. So we will use again, like in one of the exercises before, the goal seek function, and we will just use the same formula that we have used over here. At the moment this is of course 0, but that's what we will automatically calculate. And now for the remaining part of the assignment, so using the level pool routing method, which is just a calculation method, we will calculate the outflow hydrograph from our reservoir, considering that the reservoir level equals the wear level at the beginning of the storm. So as the storm flow comes in, the inflow comes in and will continue for about 24 hours, and we will get values of inflow. We know that there, based on this inflow, there will be an increase of the water level in the reservoir, and based on that increase of water level in the reservoir, there will be some outflow. The storage is changing, so that's how we can calculate this. And I've prepared this in a new sheet of our Excel file, and we see here our time, the corresponding time in seconds, and the inflow values that were given. So these are the values that are actually corresponding with our storm runoff that comes into the reservoir. And we need the equations actually, so this one again, to calculate our outflow at the outflow of the reservoir, at the outlet of the reservoir. At this right hand side, as J is unknown at the start, Ij plus 1 is given, Ij is given, and Qj is unknown at the start. But since we know that our water level is at the wear crest level at the start, we know that Sj, so at time 0, is 0, and Qj, so at time 0, Q0 is also 0. So this we can fill in already. Here we can actually, like this, we can call this storage. And this is not in cubic meters per second, but in cubic meters. And then we add also, not storage, but let's copy this one, because that's the same that we will use. Which is the left-hand side of this equation. So that will be 0 at the start as well. Now, for the next time step, we can calculate actually, we need to calculate Sj plus 1, 2 times Sj plus 1 over delta T plus Qj plus 1, based on these factors. So we say this one is equal to 2 times Sj, which will be our storage, in this case 0, divided by our time step, which was 3600, plus Ij plus 1, plus Ij minus Qj. And I've copied this in the wrong way. These are comma delimited values. So I had the wrong decimal sign when I copied this. I will replace them immediately. That will be easier than typing it each time, like this. And let's add 1 digit behind the decimal sign for all of them. So now we know that the left-hand side of our equation is 6.7, but we still don't know the corresponding outflow and storage value. But we have our storage equation, and the one that we deduced out of this storage equation, so this one. So we know that this should be equal to 6.7. So we will try to find a value of h which makes this value here correspond with a 6.7, and therefore we go to goal seek, which is what if analysis. Here we say we want to get a value for this cell for h that gives us wrong, I want a value for this cell, yeah, so for this one, so that it is equal to 6.7 by changing this cell. And if we do that, I don't have a formula yet, so that's why it's not working. I need to drag this first, that it is calculated in the correct way based on the h value. So let's do this again. So the what if analysis, goal seek, and we want to find the value of this cell equal to 6.7 by changing this cell. And if we do that, we get a value for h and a corresponding value for s and for q. So it's not exactly the same value, but it's very close, and it will give you a good representation. So we will copy s and q. They are now in the wrong order, so let's make this a little bit easier for ourselves. Let's copy this quickly over here, and let's move this column here, like that. Then we can just copy and paste these values over here. I don't want so many digits, so let's go for 2 for this one, but 4 for this one maybe, because those values will be smaller, like that. And so we have a first value for our outflow and our storage. Similarly, we can now drag this formula one down, because we can calculate these values here of our left hand side based on the previous values. So we know here 2 times Sj, Sj will be this value now, divided by 3600, plus Ij plus 1, plus Ij minus Qj. So that is correct now. Now we know that we need to find a value of 26.628. Let's copy this, like this. And so we do again the goal seek analysis. We want to change this value by saying we want it to be equal to 26.6284 by changing this cell. And so we get a value of h where we also have a corresponding value of s and q. So we fill that in over here, like this. And then again we can do the same for the next time step. So we're looking at Ij plus 1 Ij, Sj, Qj, and we get a value of 59.365. Let's copy this, go to the next sheet, and let's try to get goal seek do its work again. So 59.365 4, 6, 7 by changing this cell. And we get a new value of h, which is also already interesting to see that it is indeed in between these values here, and your 59.36 was between those two values, so it's logical that we get a value between 0.05 and 0.1, and also corresponding S and Q values. So copy that one like this. And of course we can continue like that until we have our final value. So I have continued calculating the storage and outflow values for the different values of our left-hand side of the equation. And in that way, we get a representation of the inflow and the outflow as a function of time. So now let's add a graph for this to conclude this exercise. No, we don't need the storage. We need the inflow and we need the outflow. And we did it again. Let's try this again. Inflow, outflow, and we want a scatter plot like this. Let's move this first. Call it Outflow Reservoir like this. Our titles, horizontal axis will be time in hour, and the vertical axis is flow in cubic meters per second. And the nice thing about this graph is actually that we can see, of course, the attenuation. The maximum value of our Q inflow is much higher than the outflow, the maximum outflow value. But as we are dealing with reservoir routing, it's also nice to see that our maximum value of the outflow also corresponds with our maximum value and the storage. And of course this is also what we saw when we calculated it, but here we can see it on the graph that our maximum value of the outflow actually corresponds with the point where inflow and outflow are equal. So that concludes our exercise on routing. If we look back at possible practical applications of these methods, we can of course say that in this case for the reservoir routing, this can be used to see how the water level above the crest would increase and how the flow out of the reservoir would increase based on a certain known inflow. And we need of course to take into account that there are some assumptions about the shape and about the wear crest, that the equation that might not be completely correct. But in general, this hydrological method is very well applicable for those type of problems. So if you have any problems left or any questions left about this exercise on routing, so both the Muskingum application and the reservoir routing application, you can always add a post in the discussion forum on Canvas, and then we can try to answer your question as soon as possible.